All right, well, let's continue on in our getting a more well-balanced introduction to the various aspects of programming we can be doing with a PLC. Now we're going to be talking about the sequencer and shift register instructions. So first, let's talk about the mechanical sequencers. So the mechanical sequencers are often referred to as drum switches, rotary switches, stepper switches, or cam switches. Sequencers are used to control machinery that has a repetitive cycle of operation. Useful feature, a cam-operated sequence switcher uses an electric motor to drive the cams. As the cam rotates, load devices connected to the contacts can change from on to off state, from an off to an on state, or remain at the same state. Mechanical drum operations sequencer switches, each location where there was a peg is represented by a 1. The positions where there's no pegs are each represented by a 0. So this is an example, maybe something if you've ever seen like a piano that has this kind of a mechanism to determine which keys are going to be pressed. Maybe that's a context that you've seen. For a washing machine, a dishwasher is an example of the use of a timed sequence, as are dryers and similar time clock controlled devices. And this is just giving an example of how that would look. For sequencer instructions, program PLC sequencers perform on or off patterns similar to that of a drum switch. So this is where we're getting a chance to see how that would look. So there's a handful of commands. I'll just quickly go over these. You can pause and look through them more. You have the sequencer output, the sequencer load, the sequencer compare, the file, start address for the sequencer file, mask, bit pattern through which data are moved, and destination, the address of the output word or file. These are for the SQO commands. Then we have the control length and position. The control contains the enable, the bit EN, done bit DN, and error bit ER patterns, and length is the number of steps of the sequencer file starting at position 1. Position 0 is the startup position. The actual file length will be 1 plus the file length entered in the instruction. And then we have position of the word location or step and the sequencer file from which the instruction moves data. The sequencer file, to program a sequencer, binary information is first entered into the sequencer file made up of a series of consecutive memory words. The sequencer bit file contains bit representing the output action required for each step of the sequence. As the sequencer advances through the steps, binary information is transferred from the sequencer file to the output word. Sequencers can be used to control traffics in 2 directions, and so this is starting to give you some information how that would be done. Sequencer moving data through a masked word, the masked bit mask data when reset to 0 and pass when pass data when set to 1. The sequencer output instruction requires preceding logic on the rung where it is located. Each time the rung makes a false to true transition, the position is incremented to the next step in the sequencer. For the logic 5000 sequencer output, SQO instruction operates similar to that of the logic 500 sequencer output instruction. So these are the 2 examples comparing them 1 to 1. For the logic 5000, in this here we're seeing an example. The array parameters contain the desired output state for each step. The output states are for each step is entered at the starting location in the data array. None of the outputs are energized in step 0. When the SQO instruction first executes, it will start in step 0. When the SQO instruction advances to the step number that is equal to the length parameter, it will return to step 1 and continue from there. Here's a logic 5000 time-driven sequencer output program. So now we're seeing some of the ladder logic that would be associated with this. For a sequencer programs, let's get into that. A sequencer program can be event-driven or time-driven. An event-driven sequencer operates similar to a mechanical stepper switch that increments by one step for each pulse applied to it. A time-driven sequencer operates similar to a mechanical drum switch that increments automatically after a preset time period. Here's a sequencer chart. A sequencer chart is a table that lists the sequence of operations of the outputs controlled by the sequencer instruction. For time-driven sequencer with time steps that are not all the same, this sequencer program is used for automatic traffic light control at a four-way intersection. So thus you can see that you need to have things flipped going in one direction or another, because if you have a balanced lighting mechanism that all of those parts stay the same for the same amount of time. So we talked about it before, but now we're getting into the traffic light program, some of the specifics of how you would be using the SQO and the TON for operation. For a sequencer with constant time intervals, this is what you would be using for that kind of a program. For an event-driven sequencer output program, this is what would be done for that type of an implementation, for that kind of a purpose. The sequencer compare SQC instruction is an output instruction used to compare bits from the input source file to the corresponding bits from data words in a sequencer file. When the pair of bits from the sequencer files are the same as that from the source file, then the found bit, FD, in the control register is set to 1. The instruction can be used to compare the status of a machine input device, input devices, with what is required for normal operation. And the status of the input device on the machine on or off are identical to the data stored in the sequencer file. The control found bit is set to 1. For the SQO instruction program, this gives a little bit more insight in how that could look with your ladder programming logic. The SQL instruction, the sequencer load, is used to read the PLC input module and store the input data in the sequencer file. So for example, a robot may be jogged manually through its sequence of operation with its input devices read at each step. Here's a SQL program example that you can look at if you want to pause the video and see how that works. We have bit shift registers. So here's the basic concept of a shift register. A shift pulse or clock causes each bit in the shift register to move one position to the right. The data, 1 or 0, can represent the presence or absence of parts. So you can have a bit shift right, BSR, or bit shift left, or a wraparound or circulating shift register. So those are the 3 possible shift registers that you can have. When working with a bit register, you identify each bit by its position in the register. For example, there may be a specific type of package that you want to track, and you only move 1 into the register when that type comes onto your system. On the discharge side, you may have an arm that pushes your package off the belt when the shift register shows it in the proper location, but ignores other packages on the belt. For the bit shift left instruction, the BSL, it loads a bit of data into a bit array, shifts the pattern of data through the array to the left, and unloads the last bit of data in the array. Similarly, you have the BSR. It loads the data into a bit array, shifts the pattern of the data through the array to the right, and unloads the last bit of data in the array. BSL and BSR have instructions, have the same operations. You have a file, control, bit address, and length. And so those are all the things that you would be programming. The status bits of the control word for the BSL and the BSR are the enable bit, the done bit, the error bit, and the unload bit. And you can look those over in more detail. The BSL instruction program, this gives you some ideas, some examples of how it could be utilized. With an example, I'm not going to go through this. That's the BSL. Here's the BSR, gives you perspective to think about those in comparison. And then you have the wraparound operation, BSL instruction program with wraparound. The clock pulse input is a 3-second pulse generated by an on delay timer. And so that would be a possible way of how you could use that. You can also do material handling. Shift registers are used in material handling processes when some form of binary operation must be synchronized with a moving part on a conveyor. The sensor that drives the data line on the shift register detects the presence or absence of the carton. The logic 1 sensor conditions state can indicate the presence of a carton and 1 the absence. Here we have a spray painting operation controller by a shift left register. So this is just giving you a notional idea of what it would look like. And here would be the PLC ladder logic program that would do that type of a function. Here's an example of tracking of carriers through a 16-station machine. And we can see the ladder logic for looking at that as well. For the logic 5000 controller bit shift left, that you have the array, the control, the source bits, and the length. All of those are the things that would have to be programmed in to make this function properly. And here's a BSL pass/fail inspection program, what that would look like. Okay, let's just quickly finish with the word shift operations. And so for this, word shift operations provide a simpler method of loading and unloading data into a file, usually called a stack. It can be used for tracking parts through an assembly line where parts are represented by values that have a part number or an assembly code. So this is a first in, first out instructions, how this works. And so you have the, you can have the FFL and FFU instructions are used in pairs. So we'll think about that. So the FIFO function shifts the data from a complete word rather than shifting bits of information within a word. The FFL loads logic words into a user-created file called a FIFO stack. The 2 separate shift pulses are required, one to shift data into the file, that is load, and one to shift the file out of the file, unload. And so those are the things that we have, load FFL and unload FFU. So the parameters required for the FIFO load FFL instruction are you need to have a source, the FIFO address, the control, the length, and the position. All those things need to be included. The status bits for the FFL and FFU are the enable bit, the done bit, and the empty bit. The parameters required for the FFO unload are FIFO, destination, control, length, and position. So those are similar to the FFL. So how data are indexed in and out of a FIFO file. This is an example that shows you some of those details. I'm not going to go through this, but this is in the textbook if you'd like to pursue that in more detail. The last in, first out, LIFO instruction inverts the order of the data it receives by outputting the last data received first and the first data received last. And then so we have LFL and LFU, and these would be similar to the FFL and FFU, but in reverse order of how things, this would be analogous to a queue or a line and how you have that. So you can be thinking of that. FIFO versus a LIFO, you're getting an example of those two in a picture form. So here is the LIFO instruction pair program. The LIFO stack operates similarly to that of a FIFO stack, except that the last word in the FIFO stack is the first word that is unloaded from the stack. So a computer stack would be a FIFO. If to give you an analogy, LIFO would be like a line. So the logic 5000 FIFO and LIFO instruction use tags and arrays to define the parameters. So that's what are trying to be shown here. And then just to finish up, the logic 5000 5-full instruction pair as a part of a data stack operation. This is what we're having for our last chart for this chapter. Thank you.